So a lot of these questions have to do with reconstructing the most common ancestor of two endpoints. So these endpoints could be species, could be genera. Here they're basically species. And the question is, what is the most close relative of green algae? And so green algae has a unique branch here that leads only to green algae. And then it has this branch where it connects to other branches. And so for any pair of individual species, you could find their single common ancestor. The easiest way to do that is to trace a line on the phylogeny from the species to the other species. So if we look at green algae to, first question is, let's see, green algae to red algae or moss. So we go down here, to get to red algae, along the lines, we have to trace this line and then come up this line to get to red algae. That puts their common ancestor right there. If we wanted to trace from green algae to moss, their common ancestor, to connect the dots, the farthest back you have to go in time is there. So this more recent common ancestor connecting green algae and moss says that they are more closely related to each other. And that's what we mean by more closely related, is having this more recent common ancestor. So there'll be lots of variations on the same kind of question. All right, crocodile more closely related to a lizard than a bird. Bop, 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 bop. Crocodile to bird is here, B for bird. And crocodile to lizard is L for lizard. And this question is kind of meant to upset your general assumption. If you assume that reptiles are all more closely related than any of them are to birds, turns out that's not the case. Birds are kind of an exceptional case where they have actually evolved from a reptile ancestor. So crocodiles are more related to birds than they are to lizards. Similar thing here, seals to whales. Again, you might assume something about seals and whales both sharing this ability to swim in the ocean, live in the ocean. Are they more closely related to horse or whale? So seal back here, tracing a line along the tree to get up to horse. The farthest back in time was there. And seal to whale. Seal to whale. Turns out that's actually the same ancestor. So the ancestor here was the common ancestor of all of these individuals because they all descended from that point on the tree. So this ancestor gave rise to seals, also to horses, giraffes, hippopotamus, and whales. And you would say that seals are no more closely related to any one species on here than they are to any other species because of this single common ancestor shared by all of those. All right, 5 marks on the tree corresponding to the, or which of the marks corresponds to the most recent common ancestor of a mushroom and a sponge. Same thing here. Trace the tree back in time, then forward in time. And so the most recent common ancestor of mushroom and sponge is here at D. This question of most recent common ancestor is important because C and B are also common ancestors of mushroom and sponge. So whatever this organism was farther back in time was still the ancestor of mushrooms and sponges and mice, but the most recent common ancestor is basically at this location where their two branches on the tree meet. All right, if you were adding a trout to this phylogeny, this question assumes you know a little bit about these organisms, and you can put trout into the fish category, and you also can put salmon into the fish category. And for that reason, the ancestor of all these organisms, a little bit tricky here, might be considered a fish, but we have salmon and trout. They're actually pretty similar organisms. So I think this question, a little more than the others, assumes you know a little bit more about these organisms. Salmon and trout are pretty close relatives within the fish group. So this branch here would be leading to fish, and this branch here would be leading to land animals, the tetrapod. So C would be the common ancestor of salmon and trout, somewhere along that branch, basically. All right, would you expect the common ancestor of A to look like anything on this tree? More like a rabbit, more like a turtle, more like a crocodile, etc., etc. This is something that kind of points to what we can do and sometimes some of the limitations of what we cannot do with a phylogeny. So you could have a reason to expect that A looks like a rabbit or A looks like a crocodile. Either of those could be possible. And so it's an open question, and it's not one that we can simply solve just by looking at relationships. So, for example, if there were, it's not really the case, but if there was the case where this ancestor looked a lot like a rabbit, and the rabbit inherited all of those ancestral rabbit features, then you could have that ancestor here looking more like a rabbit, and then maybe up to this point still looking a lot like a rabbit, and then becoming turtle, crocodile, or bird. That's possible, is sort of hanging on to some of these ancestral features. And another possibility is that some new features evolved along this branch to make A look like one of these things, one of these organisms farther along the tree. This is a question where you would want to use more information like fossils or more of a technical reconstruction of the features present in these different organisms. So here we have C was the best answer for this one. One cannot say without a model of how the traits evolve. All right, which of the trees depicts a different pattern of relationships? Relationships, if they are drawn the same way, show the same species having the same common ancestors across the tree. And what this is meant to indicate is that you can show the same relationships sometimes in a different way. So the basic rule is you can take any one of these branches that splits into two, and you could rotate it, and you haven't changed the relationships by rotating the branches. It's kind of like a mobile, one of those hanging ornaments. If the branches spin around, it's not affecting how things are related. What would change the relationships is if you showed species more closely related or less closely related depending on these different depictions. So for me, looking at this tree, I think one of the easier entry points is to look at this group of D and E. So D and E, these are on every tree, A, B, C, D. They're all depicted as each other's closest relative, right? So D and E share a most recent common ancestor to the exclusion of all other species. Now the third relative, their next most close relative, is C, oh no. Okay, so here we have, in this tree, they do have a close relative in C, but there's this individual B that's coming in as closely related to C, which is not what's shown on these other trees. So B with C is shown here, but B and C have a distant relative on all the other trees. So it's this one, C, that's actually showing a different relationship, mostly based on the relationship of B with C. All right, this question is meant to give you different ways that phylogenies can be depicted. So we can do the same thing as we did in the previous question, where we're finding close relatives. So ancestor at the bottom, tips at the top, D and E. That one had angled branches. This one has squared branches. This one's got an ancestor at the top and descendants at the bottom, still showing us a clade, a monophyletic group with D and E together. This one's going from the ancestor at the center, radiating outwards. And then we have, in all of these trees, we've got next most closely related species. So E and D, their next most close relative is B here. Their next most close relative is B here. Their next most close relative is B here. Their next most, oh no! Okay, so on the angle tree, D, E are shown as being more closely related to C, but in all the other trees, it's showing their most close relative as B. So A is the one that's different from the others. All right, now we've got specific characteristics on here, and it's basically, again, just another one of these path questions. If you follow the path from the ancestor, it's showing the ancestral traits, and along that path, the ancestor would have made some changes on its way to, this question asks about the seal. So if we head over to seal, we start with long tail, ears, external testes, and fixed claws. Along the way, we get a short tail, so that breaks the ancestral long tail. Abdominal testes breaks the ancestral trait. So this is an evolution, a change in the ancestral trait along that branch. And this is, again, this is the branch that leads from the ancestor to the organism of seal. Then one more, we get loss of ears, so ears are lost. And so putting these together, we would expect short tail, no ears, abdominal testes, and still fixed claws. So the place where claws are lost is over here to cats. So we need one that's short tail, no ears, abdominal testes, and fixed claws. That actually ends up being C, looks like. All right, finally, this is a plant example. Assume that the ancestor was an herb, not a tree, a herb, without leaves or seeds. So without leaves and no seeds. Based on the tree, which of the tips has a tree habit and lacks true leaves? So it says that the ancestor was herbaceous. So one thing we can find on here is where trees have come around. So these inherited the tree feature, oaks and yews. Over here, also a tree. So we have some tips that are different independent origins of being a tree. And then it also says the ancestor, let's see, lacks true leaves. So the ancestor had no true leaves. Over here we've got true leaves evolving in the ancestor of all these. And one little trick over here is we've got a loss of true leaves. So in Xylotum we've actually got an ancestor without true leaves, a descendant with true leaves, and then again a loss of true leaves. So this one does not have, I'm just going to put an X through that, I guess, no true leaves there. But over here, everything descended from true leaves that didn't lose true leaves has true leaves. And then over in this group, we have no true leaves. I guess I'll just continue the X notation here. So which of the tips has a tree habit and no true leaves? That would be this one here, the only one with a T and an X. And that's actually, it's in italics because it's a, well, it's a scientific name, but it also happens to be an extinct species. So this is an extinct relative of the club moss. Lepidodendron does not have true leaves.